Hey everybody! So here we're going with our video from today to try to do some stuff with solutions. So we'll have a few videos in this series. We're going to start off with some just sort of generics like what is a solution, what are the parts of solution, etc. And then we'll get more into, in the later videos, into some of the lovely mathy kinds of things that we get to do with solutions. So like I said, this whole chapter's got a lot of different topics into it that we're pulling in kind of from a variety of areas. So we'll deal with solutions. We're also going to deal a lot with acids and bases, so you'll hear me talking a lot about acidic and basic solutions in here. And then we'll get into types of reactions and stoichiometry here in just a bit too. So not this video, later videos, but that's where we're going. So our first part is like basically what is a solution? Just in case you're not familiar with that language, a solution is a homogeneous mixture. It's one thing dissolved in another thing. And a solution, we would say, has two components to it. The two components are the solute and the solvent. So the solute is typically what we would think of as being a salt or a sugar or whatever, the stuff that you're sprinkling in. And the solvent is the stuff that's the liquid typically. In this particular chapter, we are dealing with aqueous solutions, water-based solutions. So our solvent in this chapter is always going to be water, but you'll see on the next slide that it doesn't need to be that. So typically, again, you'd have a container of something like water, and you'd sprinkle something in there and stir it all up, and that other material would magically disappear. The solute is the stuff that seems to disappear. Again, solute is the name of that stuff. It is a homogeneous mixture, though. That's really important to remember. There are two components to this. Every solution always has sort of that background component, the solvent, and then usually the reactive component, the solute. So a homogeneous mixture here simply means that they're so thoroughly mixed together at the molecular level that you can't see the different components. Okay, just as a reminder, that solutions can be all different kinds of things. We are talking about aqueous solutions, and in most people's heads, they think about something that looks like a liquid. But it's important to remember that a solution is not a liquid. It's not a pure substance. It's a state that we have to give different set of letters to, right? AQ represents these homogeneous liquid mixtures that we've got. But solutions can also be, and there's some examples on the screen there, solids, liquids, or gases. Combinations of things can be dissolved in each other to make different kinds of solutions. So a really good example, soda, for example, is a solution that's made from a gas, carbon dioxide, dissolved in a liquid background, water and sugar and other things that are in there. So you can even talk about the air itself that we are breathing as a type of solution where you've got oxygen and carbon dioxide and farts, whatever, are dissolved in a background of nitrogen gas. So again, just as a reminder, we are dealing with aqueous solutions here, which are basically, they look like liquids even though they're not a pure liquid. And we've got something dissolved in that water is what we're typically doing. Okay, so what we want to talk about here for a minute is to get into the, well, why does water work? Water is oftentimes called the universal solvent. It's not really the universal solvent. If you've ever tried to put sand in water, it doesn't dissolve. Oil in water doesn't dissolve. But water does dissolve a lot of things. And the question is, well, why? What is it about water that makes water sort of this miraculous solvent? And it comes down to the fact that water is a type of molecule that we call polar. And we're not going to get into a whole bunch of bonding right here, right now, but there's a couple of things to know about water molecules. First of all, water does form molecules, right? These are covalently bonded atoms in here. They're sharing electrons. The hydrogen and the oxygen are sharing between them. The issue, though, is that that sharing is not equal. Oxygen's definitely a bully when it comes to electrons. Oxygen really likes electrons, and hydrogen's kind of a little tiny pipsqueak. So hydrogen doesn't really get to kind of say where those electrons go. So when oxygen and hydrogen are sharing in these covalent bonds, it's an unequal sharing. And you can kind of see it in this diagram that I have over here on the left, right? The left, correct? Because we've got our oxygen here in the middle, and hydrogen's on the outsides, kind of on the edges. And here, these little blue dots are our shared pair of electrons that's making this covalent bond. But notice how these electrons are spinning like really close to oxygen, right? They're not over here by the hydrogen nucleus. They're way over here by the oxygen nucleus. It's just so much bigger and stronger, more magnetically attractive. So what this is called is a polar bond, right? It's a covalent bond, but it's a polar covalent bond. It has ends, sort of a north and a south. Well, the symbols that they use, you can kind of see them on here. Again, I don't want to make too big a deal out of this, but you can see these funky looking little symbols right here. This one, it looks kind of like a little snake, a little spit out there. And then here's our other one down here. It looks like that. So this letter is a Greek letter. It's actually the Greek letter delta. You've probably seen the grown-up delta, which is a triangle. This is the lowercase delta. I know they don't look anything alike. Get over it. But this is a lowercase delta. And we would use that to say that this side of the molecule, the oxygen, sort of partially negative-ish, kind of negative-ish, not truly an ion because those electrons aren't over there permanently, but they spend more time there. So this is the partially negative end, and the hydrogen ends become the partially positive end. So it's polar. It's got a positive side and a negative side. And so you'll see me draw my water molecules like this all the time. So this is my polar bear. Here he is over here. You can kind of see him, right? There's his little face. There's his little ears, right? There's his little nose. Here's my little hydrogens up here, right? Like this. And my hydrogens up at the top are the positive side, and my oxygens down here is the negative side. See, now he really looks like a polar bear. And this piece is really important to understanding this partial positive, partial negative, kind of magnetic-ish feel is what really makes water a fabulous solvent. So here's why. Okay, back a little while ago, we looked at kind of the structure of an ionic substance. This right here in the middle is what you want to be looking at. See how there's these green circles that are a little bit bigger and these white circles that are a little bit smaller? This is like an ionic compound. Like this could be chlorine, Cl here, and maybe these are sodiums right here, these little NAs, right? That's like a salt molecule. These are ions. They have permanently transferred an electron from one thing to another. So these chlorine atoms are permanently negatively charged. So chlorine ions, right? The sodium atoms, a little bit smaller, right? They're kind of permanently positively charged. So what happens here is that when we have something like salt that dissolves in water, right? Well, the first thing that happens is the salt gets wet. Duh, right? Well, of course it gets wet. Well, duh. What that means, though, at the molecular level is that the water molecules are surrounding the solid salt particles that are present. And they kind of come into contact with it. And you kind of see what these little polar bears are all over the place, right? These are our little polar bears. There's our water molecules. And then here's our salt right here. So what happens here is that the water molecules hydrate the sodium and chlorine ions. They literally surround it. And so what you can kind of see here is a positive ion. Remember, this is our partially negative side of our water molecules. See how they're kind of touching that part? And then if you take a look what's happening here to our chloride ion, the positive hydrogen side is coming in contact. They sort of touch it. They gently can come into contact with it. And when they do, they form a new sort of a temporary bond. There's an intermolecular attraction. I'm actually going to write that intermolecular attraction. There you go. And what happens here is that intermolecular attraction, the attraction between the water and the ions, is just strong enough that the water molecules can sort of tow the ions away from the rest of the ions and then go swimming off into the rest of the solution. And this is true for both the positive and the negative ions. This is called dissociation, right? The ions separate and go for a swim in the nice little pool party. So you can kind of see over here some hydrated ions where these are chloride ions that are now surrounded by water molecules. And these water molecules can literally just let them go off and swim away, so to speak. And when this happens, those individual ions are so small that we can no longer see them and they disappear, right? So dissolution is like disappearing in that sense. Turns out other kinds of things will also dissolve. You guys know, for example, that sugar dissolves in water. D-glucose is a type of sugar molecule, C6H12O6. This stuff is not made of ions, but it also does dissolve. And it dissolves here, not because it separates into ions, but because there's some really important little groups over here. See these OH groups here? By the way, in these sorts of drawings, the red ones are always oxygen, the white ones are always hydrogen, the black ones are always carbon. So you can kind of see we've got these bonds out here, these little groups sort of hanging off on the edge. And these little ones off on the side, these hydroxide groups, OH groups on the edges of molecules, those are other little spots where water molecules can come in and sort of be temporarily attracted and form those intermolecular attractions at these hydroxide bonds, or hydroxide groups. So again, it doesn't have to be ionic to dissolve, although being ionic helps. But things like this that have these polar groups can also dissolve pretty easily if they have hydroxide groups on there. Again, those are strongly polar and strongly attracted to other water molecules that's on there. I'm going to come back to this one in our second episode. So there you go. That's it for our first one. So we've got some kind of ideas about how solutions form. Solute, solvent, makes solution. And now you have a little bit of insight into how dissociation happens, how water molecules can sort of temporarily attach to or be attracted to different ions and pull them off, or potentially even here with something that's molecular and allow that to dissolve as well. So I hope you liked it. I'll see you in the next one where we'll talk about electrolytes, as you already saw.